Okay, so just a reminder that Friday is the midterm. I'm sure you guys are all really excited about that. Yeah. If you could please show up early, bring your ID, we'll scan you on the way in. There are 440 of you taking this class, so we will be at capacity. So when you come in, please try and fill in from the center of the rows and don't leave any spaces. If you can also try not to bring a bag if you don't need to bring a bag or leave it somewhere else. You can bring it in, but if there's over 400 of you trying to leave bags at the front, it's going to be a bit chaotic. Okay, so if you don't need one, please try not to bring it in. You won't need a calculator, and calculators aren't allowed. Everything should be left in calculator ready form. I distributed the formula sheet last week. There was an announcement called Midterm 1. So if you've not seen that already and you want to see what the formula sheet is like, it's in there. That'll be printed in the book, so you don't need to bring anything in with you. No cheat sheets or anything like that. Any questions? Anything I've not covered? We're going to go for a 45-minute midterm as well, just because there's so many of you. Okay. So the question was, are the questions going to be exactly like we did in class? They're going to be pretty similar. So quite a few people have asked me in terms of what should I be using as my practice or as my revision. The questions are going to be very similar to the kinds of questions we do in problem classes, the kinds of questions that were on the IQs, and to a certain degree, some of the OQ questions, and some of the self-study questions. The textbook ones are a little bit different in places, but the wordier questions rather than here's a function differentiator, okay? It's going to be more placed in some sort of biological context. Any other questions? Yes, sorry. There's 3 questions split into different parts. Okay. You guys are lucky. I made the midterm last summer, the first one way too long. So I've learned my mistakes, and this one is definitely shorter, okay? Any other questions? Okay, so today we're just going to go through a review of some of the material, and that will give you a bit of a hint as the kinds of things you might be expected to do on a midterm, you know, if there was one coming up. So I put some, as usual, I put some problems online. I'm going to skip over the vector one to start with and come back to it if I have time. I'm going to focus on the wordier problems about population models and linearization, and then go back to the vector stuff if I have time at the end, okay? So this kind of problem, we've met many times before. We've met it on the IQs, we've met it in class, in the lectures as well, in the pre-recorded lectures, that is. I just want to go over again how we take a word problem like this of a population model, turn it into some linear equations, how we then put that in matrix form, and then ultimately how we determine the long-term behavior, okay? So I'll start going through this one with you guys, and then I'll get you guys to do the eigenvalues, okay? So here we're told that a species of barn owl can be divided into 2 age categories, juveniles and adults. Each year, the adult population produces an average of 3 offspring each, and a quarter of each population dies. Juveniles take 4 years on average to mature into adulthood. Okay, so the first part is to write down a linear system of equations that describe the change in the state of the population from one year to the next. The very first thing I need to do is to define what my variables are, okay? Don't just write down X's and Y's or whatever and assume that I know that that means juveniles and adults. Whatever you choose, make sure you define it. So I'm going to let Jn be the number of juveniles in year n, and likewise An, the number of adults. Yeah. Don't forget to define your variables. Okay, so let's write down how we're going to get to juveniles in the next generation based on what we have currently. Okay, so first of all, I'm going to start with all of the juveniles. So that's a proportion of 1. And then we're going to subtract juveniles that are either maturing into adults or those that are dying. Okay, so what do we know about maturation? we're told that juveniles take 4 years on average to mature into adults. So that means that all else being equal, on average, we're going to have a quarter of them maturing each year. We're also told that a quarter of each population dies each year. So we have minus another quarter. This is going to be times by our population in the current year, Jn. What else do we need to add on to our juvenile equation? Anyone? Production of offspring, thank you. So births. So this is going to be the contribution of adults to the juvenile class is going to be births. So told that each year the adult population produces an average of 3 offspring each. So across 3 AN. So just simplify that down. So that's a half of Jn plus 3 AN. So that's my juvenile equation. Then my adult equation. What are we told here? Well, we were told that juveniles take 4 years on average to mature into adulthood. That was this one here, I believe. Doesn't matter because they're both a quarter. So we need to have a quarter of our juveniles appearing in the adult equation. And then we need to have adults who are staying adults. In other words, adults that don't die. We're told that a quarter of each population dies. So just like the juveniles, we're going to remove a quarter of the adult population. So we can write that as a quarter of Jn plus 3/4 AN. So another way of thinking about these things is about flow. And we're going to talk at the end of this course about graphs and then come back to ideas about population models as part of that. You can think about your juveniles and your adults visually like this and think about the flow between these classes, okay? So one way in which we can represent that is the flow from juveniles to adults, the flow from juveniles to juveniles, and the flow from adults to adults. So think about the start of these arrows are representing what you have initially, and then where they're going is their contribution into whichever class, whether it's contribution to juveniles or contribution to adults. So we could represent this as, for example, a quarter of juveniles are maturing. So the arrow going from J to A has a quarter on it. Births is 3. So we have the arrow from A to J is 3. We have 3/4 of our, oh no, sorry, a half of our juveniles are staying juveniles because a quarter of them are maturing and a quarter of them are dying. And then we have 3/4 of our adults are staying adults. Okay, so if it helps, you can represent the information visually. This might be a good intermediate step that you want to do before writing down your linear system of equations. You don't have to do it, but some people find visualizing this helps before going into equation form. Okay. Okay, so we've got these linear systems of equations. As you know, we can write this in matrix form. So now we want to write it as a matrix equation. Again, we need to do a bit of definition first of all. We need to define our population vector. So I'm going to define Pn to be the vector Jn AN. It doesn't matter which order I put these in as long as I'm consistent, okay? Then what are we going to have? We can write down population state in the next generation, Pn plus 1, is going to be our Leslie matrix given by the coefficients times by the population state in generation n. This is going to be my Leslie matrix. And the coefficients just come from above. So remember, everything on the main diagonal is everything that's staying in that category. So we have a half and 3/4. Everything below the main diagonal, because I've got things ordered young to old, is going to be aging. So that means this quarter here goes down here. And then I have births in the final spot, which is 3. So you might find as well when you're writing down your linear system of equations to write them in the order that you intend to put your population vector. So you notice above when I wrote down my JN plus 1s and AN plus 1s, I put the JNs first, then the ANs. I could obviously write them around the other way, but it doesn't matter. Yes, sorry. As in, if you had just written down Jn plus 1, An plus 1 is equal to this, do you mean? Yes. You can do that. The reason I've defined it as a population vector here, just for later notation, really. So, I mean, it's the same thing if you write down a vector with Jn plus 1, An plus 1, rather than writing down what Pn is here. If the question asks you to define the vector, then you should define that as a vector. I've lost my train of thought. What was I saying? I was writing them down in a particular order. Okay, so you'll find it helpful if you write them down in the same order as you intend to put them in the matrix, because then you're just lifting out these coefficients. You know, just go to half, 3, a half, 3, a quarter, 3/4. I just write them straight down below. The other thing you can do at this stage, if you want to make sure that you've written down things correctly, is this Pn, remember, is just my Jn An. So I can multiply out my Leslie matrix by this vector and check that I get the right thing. So check that I get the system of equations that I started with. So if I do that, I have a half of Jn plus 3 times by An, which is what we have above. And then on the second row, a quarter of Jn plus 3/4 times by An. Okay, so your matrix multiplication will help you check that you have got the right thing. Okay, so now we've got our matrix equation. Here we want to find the eigenvalues and corresponding eigenvectors of this Leslie matrix, and then hence determine the long-term behavior of the population. Okay, so I'll get you guys to work out the eigenvalues, and then we will check in. If you finish that, carry on and work out what the eigenvectors are as well. And then we'll talk about what it means in terms of long-term behavior. Okay, let's see how you guys got on. There's quite a few questions on this stuff still. So questions again about ordering. So just to recap here, it doesn't matter which order you put your JNs and ANs, as long as you do the same with your rows in your Leslie matrix, okay? And likewise, that means that the interpretation of the different elements in this Leslie matrix depend on the order of your population state vector. So because I'm going young to old, juveniles, then adults, that means that this term here is births, and this term here is aging. If I did adults, then juveniles in my population vector, the term in the top right would then be aging, so I'd need to have a quarter there, and this one down here would be births, that'd be 3. Everything on the main diagonal is always everything that's staying in the same category, okay? But again, if I switch the order around, then rather than it being juveniles, adults, it would be adults, juveniles, okay? So just make sure that you're consistent with how you order things. Generally speaking, I'll put things as young to old because that's the easiest way of thinking about it. Let's work through eigenvalues and eigenvectors. A few people asked what if you're having to solve a quadratic equation, for example, on a midterm, there's a slight hint. The numbers that I have chosen, if I have chosen, are much easier, okay? So you don't need calculators for them. They should be things that work out very nicely, okay? So how do we work out our eigenvalues? We need to take the determinant of our Leslie matrix minus lambda, where lambda is our eigenvalues times by the identity matrix. We're going to set this equal to 0. Okay, so just to write this out in full, we want the determinant of a half minus lambda, 3, a quarter, 3/4 minus lambda. You should know how to do your determinants by now, but it's the product of the elements on the main diagonal minus the product of the elements on the off diagonal. So what's that in this case? We've got a half minus lambda, times by 3/4 minus lambda minus 3 times 1/4, so that's 3/4. And we're setting this equal to 0, so we have a quadratic equation in lambda. So at this point, we can expand it out. So you have lambda squared minus 5/4 lambda minus 3/8. You can factor this one, so you can factor it into lambda minus 3/2, lambda plus 1/4. And so that means that one of our eigenvalues is 3/2, and the other is minus 1/4. Okay, these numbers were a bit nastier than what you might see on an exam. Yeah.
What is be that precise? Like how to say words? As in, like, do you want us to factor it out, or it's leading quadratic equations, even if
I mean, if you get there will be partial marks, right? So you'll get a mark for getting to this stage, right? If you got stuck at that point and didn't know what to do, you would still get some partial marks.
It's like what you do, plus minus some value.
Yeah.
Not the equivalent marking to figure it out.
I'm not sure I quite follow your question. Are you saying if you'd use, say, the quadratic equation to solve this, so your lambda is equal to minus? Yeah. Yeah. If you'd ended up with something in calculator ready form, that's also fine. Like I said, the ones in the exam would be a little bit easier than the ones here. Okay. I know that you guys have calculators here, so that's why it's a little bit more complicated than this one. Okay, so you have lambda, one of your eigenvalues. Again, it doesn't matter whether you called lambda 1 minus 1/4 and lambda 2 3/2, or you've got them like I have here. You should end up with 2 eigenvalues like this. Can I have a show of hands who got this far? Okay, fantastic. Yes. Have a little bit quiet, guys, because I can't hear questions. Yeah, that was expanding out this. So you would end up with a 3/8, a positive 3/8, minus 3/4, which will give you minus 3/8. So that's how you get from there to there. Any other questions? I thought I saw a hand go up somewhere over here. No? Okay. So we've got our eigenvalues. Now we need to work out our eigenvectors that correspond with those. So we need to work through in sequence. So let's start with our first one. Lambda 1 is equal to 3/2. How do we work out our eigenvectors? Well, we need to look at the matrix L minus lambda 1, so minus 3/2, times by our identity matrix. And when we take that and multiply it by our eigenvector, which I'm going to call V1, we are going to get a 0 vector. Okay, this is always the case. This is what it means for it to be an eigenvector and an eigenvalue. So we can work out L minus 3/2 times by I. If we do that, we're going to have from about half minus 3/2, 3/4, and 3/4 minus 3/2. So that's my L minus lambda I. That's my vector, my eigenvector, and that's going to be the 0 vector. So what does that give me? Minus 1, 3/4, minus 3/4. That's my matrix. When you do this, these rows are always going to be multiples of each other. So at this point, you can expand out and solve these equations simultaneously. You're going to have 2 equations in 2 unknowns, but they're multiples of each other. So actually, you just have one equation in 2 unknowns, which means you have to fix one of these things to give you the other. This is why we always end up with an infinite number of different eigenvectors, is because essentially we're just picking values along a straight line. The trick that I told you guys is that we take on one of these rows, I'm just going to pick the first row here. We take these coefficients, the -1 and the 3, and we flip the order of them and change the sign of one of them. So if I do that, if I put what was in front of the second term, there's a 3, that's going to be now my first term. I had a -1, that's going to in front of my my first variable, so that's going to go into the second position now, and I'm going to change the sign of that. I could have changed the sign of the second one and had -3, -1. I could have had any non-zero scalar multiple, and that would have been fine as well. I could have done it by the second row if I wanted to. So this is my eigenvector for my first eigenvalue. Okay. The reason this works, just a quick recap on that. If I called my V1 xy and expanded this out above, I would get -x plus 3y is equal to 0. That's if I just expand this out here. So as long as I take this and put it here, take the coefficient here, which was -1, change the sign, and put it here, this will always equal 0. So this is why this trick always works. So if I set x to be 3, I'm going to have -1 times by 3, which is -3. If I set y to be 1, I'm going to have +3. So I have -3 plus 3, which is equal to 0. So this is why this always works. Okay, so that's my first eigenvector. The second one. So for λ2 is equal to -1/4, we do exactly the same thing. So we need to look at L -1/4 times by I times by my eigenvector, and that's going to be 0. Okay. So if we fill this out, we'll end up with 3/4, 3/4, 1 times by my eigenvector is equal to 0. I can do exactly the same again. This time I'm going to choose the second row. So we can end up with V2 here being equal to, switch the order around. So 1/4. I need to change the sign of one of these. I'll just put it in front of the quarter here. So we have 1 -1/4 is an eigenvector.
So if you can both of them be negative? Like,
Yeah, exactly.
Originally negative and this the other side. That's fine.
Exactly. So in this first case up here, I could have had -3, -1. It's because we have an infinite number of eigenvectors, right? And they're only unique up to non-zero scalar multiplication. So you can't multiply them by 0, but you can multiply them by -5 or pi or whatever you want to do. Okay. Okay, so we've got our 2 eigenvectors here. Let's just go back to what the question asked. We're told to work those out and then determine the long-term behavior of the population. Okay, so whenever you see long-term, you need to think eigenvalue, eigenvector. Okay. The fact that we've got these 2 eigenvalues here, if I just go up here for a second, we've got λ1 is a 3/2 and λ2 is -1/4. So we have that λ1 is dominant because it's bigger than the magnitude of λ2. Okay. What that means when we write out our solution, that in the nth generation, that our solution for n very large is going to tend towards some constant C1 times by λ1 to the n times by our eigenvector V1. Okay. So we don't care about any of the other eigenvalues or eigenvectors. When n gets very large, as n tends towards infinity, our solution looks like this. So our eigenvalue and our eigenvector tell us 2 different pieces of information. Our eigenvalue here tells us whether the population is growing, tending towards a constant, or shrinking. The reason being that if λ1 is greater than 1, then we're taking something greater than 1 to the power of n. So that's going to get bigger and bigger and bigger. So the population is growing. If λ1 is equal to 1, then we're taking 1 to the power of n. So it's just going to be 1. So it's tending towards a constant population size. If λ1 is less than 1, taking something less than 1 to the power of n, as n gets very, very large, that tends towards 0. So the population is shrinking, it's going to go extinct. Okay, so this eigenvalue, the dominant eigenvalue tells you whether it's growing, tending towards a constant, or shrinking. And then the eigenvector that corresponds to the eigenvalue. So here, this is my V1, just here. This tells you the ratio of our different classes. So it's going to tell you in the long term what proportions are you ending up in the different classes. So here I could just say we're going to have a ratio of juveniles to adults of 3 to 1. So I know that my population grows because lambda 1 is greater than 1. And I can tell that my long-term ratio of juveniles to adults is 3 to 1. Okay, so that was nice to do because there was already a 1 here. The other thing I could do is, because our eigenvector is only unique up to non-zero scalar multiplication, I can rescale this if I want it in terms of proportions. Okay, so if I sum up the elements in this eigenvector, 3 plus 1 is 4, I could have written this, I'll call it U. I could have written this as 3 over the sum, which is 4, and 1 over 4. Okay, so if I add the terms up, divide by the sum, note here, this is always then going to equal 1. So that tells me that in the long term, 3/4 of individuals are going to be juveniles and 1/4 are going to be adults. Yes. That is a good question. It's a little bit more long-winded, so I'm not going to go into that now. It's a good question, but everything that you will meet here we won't fall into those scenarios. Okay. Yeah, it's too long-winded to kind of go into now, but it is a good question. Any other questions? Yeah. Sorry, guys, can you be quiet? I can't quite hear. Yeah. I'm not quite sure. Come up to me after class and I can go through your working and tell you what happened, okay? Any other questions? Yeah, at the back. Sorry, can you say a bit louder? What, for my long-term behavior? No, so our long-term behavior, we only care about our dominant eigenvalue and dominant eigenvector, okay? So this thing down here is telling me that in the long term, when n gets really, really big, we only care about our dominant eigenvalue and eigenvector. So this down here in pink, we don't care about that and we don't care about that at all. Okay, so we only care about our dominant one, which is lambda 1 and p1 here. Yeah. It doesn't matter. I mean, if the question, for example, asks for it in proportions, then you want to rescale it like this so that they sum into proportions. If I ask for a ratio, you might want to do it something like this so that you have integer values, so it's nice and simple. Okay. They're the same thing. It just kind of, it depends on what your, okay, let me say it slightly differently. There's a mathematical representation here of your eigenvectors, and you can have any non-zero scalar multiplication. However, writing them in a certain form makes the biological interpretation easier to understand. Okay, so there's many ways that we can write things mathematically, but there are a fewer ways that we can write things biologically that make sense. That's basically the key point. Yeah. The C is just some constant. That's a good question. So where does this C come from? The C depends actually on our initial conditions. Okay, guys, bit quiet, please. So this C here is just some real number. It depends on our initial conditions. And the reason we have that there is because you can have different initial conditions which will affect what your population looks like eventually. Okay, so it doesn't matter in terms of the long-term behavior because there's no power of n here. But this is referred to as our general solution, and we'd have a specific solution if we gave a specific initial condition. Okay, good question. Okay, guys, I'm conscious that we have focused on this one question. I do want to talk about linear approximation. If you have any other questions, you can try and ask me after class at this time, but seeing as we've only got 10 minutes, I do want to go through this as well. Okay, so here we talked about, very recently, we've talked about linear approximations and tangent planes. Here we've got an example where a researcher estimates the fitness in F of a population of lions. We have lions' length in meters and weight in kilograms, and we have some measure of its fitness, okay? And we're asked here to find a linearization, Y of L and W, around a point, or at a point, 1.9 meters in length and 200 kilograms in weight, okay? So how do we do this? Well, we need to look at our partial derivatives. So what's our F sub L? In other words, what's our partial derivative of F with respect to L? I'll work through this one with you guys, seeing as time's short. So remember when we're doing partial derivatives, whatever we're not taking a derivative with respect to, we treat it as a constant. So here we're treating our W as a constant. So we're going to have 1 over W minus W squared over 100 e to the minus L over 100. Okay, so we had a minus 1 over 100 times by our L in our exponential. So that minus 1 over 100 comes to the front. We can do the same thing for our partial with respect to W. So now L is going to be a constant, and we take our derivative with respect to W. So here you're going to end up with minus L over W squared plus 2W e to the minus L over 100. Okay, so those are our partials. Those are the general forms of our partials in terms of L's and W's. We're interested in these partials at this point given by our L and W's. The next thing we can do is substitute those values in. So what is our F sub L at 1.9200? If you work that out, which I'm not going to do here, obviously, because it's a long calculation, that's plugging things into a calculator. minus 392.47. And in this case, if we do the same for our W, evaluate it at the point of interest. In this case, it's 392.47. Nice bit of symmetry there, actually. Okay, so the last thing we need as well is we need our function to be evaluated at this point without taking the derivatives. So that's just plugging values into this initial equation here. If you do that, you should get something, I think 392.4.7. What these values are doesn't really matter for this example. What matters is what the process of what we're going through, okay? So what is our linearization? Our linearization of our function y, LW, so y is just our linearization. Yep, before I carry on. That's 3,924.7, unless I've made a mistake. If I've made a mistake, then please let me know. Hopefully that is the right value. I'm copying it down from solutions that are already written down here, so hopefully that is the right value. What for the derivatives versus here? So in the derivatives, obviously our derivatives are different from our function value. So there's no reason why they would have to have decimal points in the same place. Assuming this is correct, I'll check after class, but assuming this is correct, regardless, we write down our linearization as our function value evaluated at that point. So in this case, f of 1.9200 plus our partial with respect to L at that point. So this is telling me how much I'm changing as I move in the L direction. So how much of an effect is the line's length having on its fitness? So we take that gradient in that direction and multiply it by how much we move in that direction. In other words, what is the change in our length? The point that we're starting at is 1.9 meters, and we might change its length to be more or less. Either way, we multiply by L minus 1.9, okay? So whatever our variable is, L minus what our point was to start with. And then we need to do exactly the same for the other variable with the f of w. So our partial f sub w evaluated at 1.9200 is telling me how much the line's weight, the change in line's weight at 1.9200 affects its fitness, okay? And we multiply that by how much we're changing in weight. Okay, so we could expand this out. I'm actually just going to leave it in that form now. We can use whatever the values are, it doesn't really matter here. The key thing is making sure that we end up with this form for your linearization. Okay, so the linearization is on the formula sheet, but make sure you understand what the interpretation of these different terms actually are. Okay, so at this point, we could approximate the fitness of a line that is somewhere nearby. So remember, this linearization only applies, it's only a reasonably good estimate when we are nearby. If I took, say, a line cob that was only 0.2 meters long and weighed 10 kilos or whatever, it wouldn't be a very good estimate, okay, because I'm very far away from where I've taken my linearization. So these only work when we're close by. So we do a linear approximation. We say that our function, our fitness at this value, 1.95210, is approximately equal to our linear approximation, so our linearization at 1.95210. Okay, so you can substitute this in. If you do that, you should end up with 4315.2. This is just a value, okay. What we can do though is we can compare this value to our function value. So we know, I'll do it in a different color. So we have this, our initial lion that's 1.9 meters long and has a weight of 200 kilograms. And we've approximated the fitness of one that is slightly longer, 1.95 meters and slightly heavier, 210 kilograms. The value that I've got out here for this fitness function is higher, which tells me that the larger lion is fitter in this particular case. Okay, so that would be the conclusion that I would draw from this type of model. Okay, I'm conscious that quite a few people had questions. So what I'm going to do is there is a question on vectors at the start that is simple arithmetic. The solutions for that will be online. What I'm going to do is I'm going to end there. And if you have questions, you can come and ask me and that'll give you a bit more time, okay? If not, see you on Friday.